This lesson is for section 8.3. We're going to be graphing transformations of our sine and cosine graphs. So our objective for today is to actually graph functions of the form y equals a times sine of bx minus c plus d and y equals a times cosine of bx minus c plus d. So we're seeing transformations of the graphs that are slightly different than what the title suggests. Here they're missing that plus d in the title in your textbook, but we're just adding one more transformation. We are also going to be talking about the amplitude and period of our functions after they've been transformed. And we're going to discuss this new vocab word here, the phase shift of our cosine and sine function. So before we even begin graphing any of our transformations here, I want to make sure that we have a really solid understanding of these terms here. And the fact that these two graphs here are really just transformations of our mother functions, sine of x and cosine of x. So we need to know what these basic graphs look like, which is what we studied yesterday, before we can begin to understand what these different parts here will do to transform our mother function. All right, so here's a general sine curve. Now our mother function has an amplitude of 1, so you see a max height of 1, a minimum of -1, and our period here is over 2 pi, so our period is 2 pi. Now, if I change the value in front of this function here and I put this 2 here, like we saw yesterday, that will cause a vertical stretch here, and now my amplitude will change to 2, giving me a max height of 2, a minimum of -2. But overall, my period remains the same. If I place now a 1/2 out in front, you're going to see that this is now compressed vertically. So now we have a smaller amplitude. It's 1/2 now, so we have a max height of 1/2 and a minimum of -1/2. The period, again, still stays the same. So that a value out in front just makes it, the amplitude adjusts, right, which is basically a vertical stretch or a compression. Okay, so here we are again with our general mother function here for the sine curve. Now, if I place on the inside here 2, so this is basically representing the b in our general function when we look at our transformation. So this is a b value here. If I now highlight this line, you can see that we are now compressing this horizontally. So the period has changed. It used to be 2 pi, right? The red function here has a period of 2 pi, while our green one has a period of just pi. So this is called a horizontal compression, okay? If I now place a 1/2 out in front, this is actually going to cause a stretch, a horizontal stretch. So I'm going to highlight this one real quick. So now you can see I can't even actually fit the entire wave. If I zoom out here, now you can see that our period has doubled, right? So our period has doubled here. Now it's 4 pi for y equals sine of 1/2 x. Okay, so again, to review what we talked about from yesterday, this a value affects our amplitude, right? It's going to adjust our overall max height and min height because it'll either create a vertical stretch or a vertical compression. Now, when you have an equation of the form y equals a times sine of bx, which is what we looked at in yesterday's lesson, this is going to cause either a horizontal stretch or a horizontal compression. So now we've got this different term here, this bx minus c. Okay, so this is going to affect our graph even more. Now, bx minus c here determines a phase shift. So we call it something different. We call this a phase shift, and it shifts our graph horizontally. So everything is affected horizontally by bx minus c. So the b and c combine together to shift our graph horizontally. So let's take a look at what that would look like. Okay, so we're back to our mother function again, and I know I keep using sine of x, but remember this also still applies to cosine of x. The transformations and the effect of a, b, c, and d are all the same for our cosine graph as well. Now, if I have this -pi/4 on the inside here, this is actually going to shift everything horizontally, and it's going to shift everything horizontally to the right pi/4 units. So you're going to see here our blue graph. If I try to find that intercept here, so we start off at 0, 0, right? That's the coordinate 0, 0. Now I'm at pi/4, 0. So everything has been shifted right pi/4 units. If I take a look at our maximum here, which was at pi/2, now it's going to be at 3 pi/4. So everything again is shifted over to the right, exactly pi/4 units. Okay. Now it shouldn't be a surprise then when we see x plus pi/2 here on the inside of those parentheses, that everything's going to be shifted left pi/2 units. So when I graph this guy, it's harder to see here, but if I just go back here so that you can see this coordinate 0, 0 has now been shifted to -pi/2, 0. Okay, so again, everything shifts left now. So it really has the opposite effect. okay, on the inside there. But this is, again, just a horizontal shift. So we haven't seen any type of stretches or shrinks. It doesn't affect our period at all either. If you look, our overall period for these functions is still 2 pi, okay, whoops. But now when we add in this term here, so this is really like what we're seeing in the bx minus c here. When we have both a horizontal shift left or right and a vertical compression and stretch, it's going to do something a little bit different. So let's look at the purple function in relationship to the green function, because these are very close to one another. So let's get rid of these two here. All right, so if I look at that green function here, remember it started at negative pi over 2. Well, our purple function does not share the same value, right? The y output is not the same, and that's because when you have both a vertical shift left or right and a horizontal compression or stretch, now it affects where you start, and it also affects your period, of course. But we have to make sure that when we graph this, we take that into account. So we'll figure out how to graph this by hand, but I do want to show you one more transformation too, and that's this next one here, which is this plus 2. So hopefully you're remembering when we did, transformations of functions before, anytime you have a plus something on the outside, this would be representing our plus d in our general, sine and cosine functions. This is going to transform this by moving the entire graph up 2 units. So if you look, now I see that the coordinate, let's start with the one that I guess is already highlighted. 0, 1 has now become 0, 3. So every single coordinate here in that purple graph has now been shifted up 2 units. So of course if that was minus 2, then it would shift it down 2 units, okay? Now the last piece of information I want to talk about is another vocab term, and that's the equilibrium axis, or sometimes called the midline. So either one is interchangeably, it means the same thing, but the midline of the graph is where you have your intercepts. So it's where that sine function here, if we look at our mother function, our sine function here is centered at a midline of y equals 0. Okay, that's our midline or equilibrium axis. But when we look at this function here, our midline or equilibrium axis is not, it's no longer at y equals 0, it's actually at y equals 2 here. Okay, so y equals 2 is our midline or equilibrium axis. It's where that graph is centered, basically. Okay? Alright, so now that we're familiar with all this terminology here and the effects of a, b, c, and d on our graph, let's begin with our first function here. It says to sketch the graph of y equals 2 times the cosine of pi x. I'm going to begin the problem here by just sketching our basic graph here, y equals cosine of x. So I'll just graph the mother function first. You don't have to do this on every single problem, but I think it might be helpful for you on a test just to have that at the top of your paper. But we go from 0, 1, we go through, back up, and we come back here, and we end at 2 pi. So that represents one full period for our cosine graph. So here we have pi, 3/2 pi, pi over 2. Now our maximum, since our amplitude is 1, will be 1, and our minimum will be -1. So there's our basic cosine graph. Alright, so I know that my new graph should take this general shape, right? But I don't exactly know where it starts and where it stops, where we have one full period. So what I'm going to do is trap this angle here between 0 and 2 pi. I know that for cosine of x, this is always going to start and stop at 2 pi. So that's why we have one full period of 2 pi, right? It completes its general shape. Now I want to know the same thing for pi x here, the 2 times cosine pi x, and I'm going to trap it between 0 and 2 pi to see what happens between those two values. So I have 0 is less than or equal to pi x is less than or equal to 2 pi. So again, I'm trapping pi x between these two values, okay, 0 and 2 pi. So if I solve for x here, and I isolate my x, I divide by pi on both sides here, I end up with 0 is less than or equal to x is less than or equal to 2. What this is saying is that our function will start its basic shape at 0 and end its basic shape at 2. So when I graph this now, I'm still at a horizontal, I'm still on my y-axis here at 0, but this time it'll be 0, 2. So it begins again at 2, I'm sorry, it begins at 0, then it goes through here and comes back up, but it finishes its value here at 2. Okay? Now that makes halfway point here 1. The intercepts would be the the distance that is split between 1 and 2, so 3/2, right? 1 1/2. And this coordinate here would be at 1/2, 0. So that's 1/2. So our max has changed to 2, and our min has changed to -2. And this would actually be my final sketch here. Okay? So let's go on, and I think this might be a little hazy right now, but we'll clear that up here with the next graph. So here we've got sketch the graph of y equals -4 times the sine of 3/2 x plus pi over 2. So now we're seeing a stretch as well as a horizontal shift left or right. Okay? So let's start with our general shape again for the sine function. We know that it's going to look like this over a period of 2 pi. Here's pi, here's 1, here's -1. Okay, so that's our general shape. Now, this is going to flip our shape. So I know I'm going to start with a shape that now looks like that. So I draw that in actually first. Okay, I begin by just drawing that. So I've taken care of this, that negative. I also know that my max and my min is going to be at 4 and -4 because the amplitude has changed. But I actually don't want to draw in my vertical axis yet, because I don't know where it's going to start, right? I don't know that this point here starts at 0, 0. I just don't know that yet. So what I'm going to do again is trap this in between 0 and 2 pi. So I have 3/2 x plus pi over 2 trapped between 0 and 2 pi. So I'm going to figure out where this begins and where it ends by solving again for x. So I would subtract pi over 2 on both sides. So 2 pi minus pi over 2, that gives me 3/2 pi. And now I'm going to solve again for x by multiplying by 2/3 on both sides here. So if I multiply by 2/3 here, I end up with -pi over 3. If I multiply by 2/3 here, I end up with pi. So what this is now saying is that this value here, where I start, is actually at -pi over 3. Okay, start at -pi over 3. I end at pi. So let's figure out where this point is now. What we're looking for right now is the halfway point between -pi over 3 and pi. To find that, you want to find the overall distance between those, take that in half. Now that doesn't give you the actual halfway point, but it gives you, the distance here. It will give you that, and then you can subtract that from pi, or add that to -pi over 3 to figure out what that halfway point is. So let's do that calculation real quick. So I want to find the overall distance between pi and -pi over 3. So I'm subtracting -pi over 3, which is really like adding. So I have 3/3 pi plus pi over 3 to give me 4/3 pi. Okay, so there's the overall distance between those two. Now if I cut that in half, so cutting it in half is really like multiplying by the reciprocal, I have 4/6 pi, or 2/3 pi. So that's saying that this distance here is a distance of 2/3 pi. The distance here is a distance of 2/3 pi, which would make this coordinate then, you got to be really careful that you don't just call it 2/3 pi, because you want to add that to the -pi over 3 here, or subtract it from pi. Either way, you're going to end up at pi over 3. So this is really pi over 3. Now you want to find, so we want you to be specific too about where your, that's actually probably good that that thing got erased because I need to redraw it so it's a little bit nicer anyway. Oh, that's still terrible. Okay, but anyway, we want to make sure that we find our max and mins here and where those occur. So let's find that. Now, that again is going to be halfway between these two values here. So we'll take pi minus pi over 3, right? We get 2/3 pi. That would be the distance between the two. Let's cut it in half. Obviously, half of 2/3 pi is pi over 3. So we're going to add a third pi here to that pi over 3 to get to 2/3 pi. Okay, add a pi over 3 here to get to 0. So actually, we would want to draw in our horizontal axis here. Okay, so that's the line. This is our x-axis, this is our y-axis. So that's why I didn't want to draw in the horizontal, or I mean our vertical axis right away. Okay, so again, you got to be careful that you're not just calling this, the coordinate that you're trying to find. You have to make sure that you're adding that. Now, obviously, a lot of this could be done in your head. I'm just showing you the work in case you're uncomfortable doing it with the fractions. When we did this one over here, this was really straightforward because we can cut two in half, and then we can cut 1 in half and do that really quickly. But when you're dealing with these fractions and the pi's and stuff, I understand that it can be a little tedious to do, but that's really all you're doing is cutting these numbers in half and then subtracting or adding those values, okay? So the last thing I have to make sure that I do on the graph is just showing the max and min heights. So here I've got a max of 4 and a min of -4. This is my sketch. I am donezo after showing all of these important values. Okay? Alright, so number 3 is a big mama jamba, a fatty boomba, if you will, because it's got all these transformations going on. Okay, it's the most complex one that we've seen so far. So let's start with graphing a horizontal line here, which is not necessarily going to be the y-axis because we are translating this up 4. But anyhow, the general shape here will look like this because of the reflection, right? That negative sign here. Okay, so let's figure out where our little graph here begins and where it ends. So let's trap 3x minus pi over 3 in between 0 and 2 pi. I have no idea how that changed color. That was weird. Okay, so anyhow, let's add pi over 3 to both sides. So that gives me 2 pi plus 1/3 pi is 7/3 pi. Let's divide by 3. So we have pi over 9 is less than or equal to x is less than or equal to 7/9 pi. Okay, so I have one full period then. The difference here would be 6/9 pi. Right, that would be my period, which let's simplify to 2/3 pi. Okay, now let's draw that in here. 7/9 pi and pi over 9. Now I can draw that y-axis in because I know it'll be to the left of this. Okay, now let's find this coordinate. So we know the general distance here, or the overall distance is 2/3 pi. If we cut that in half, let's keep it in terms of 6/9 though, maybe that'll be easier for us. If we cut this in half, we end up with 3/9. Okay, so I would want to subtract 3/9 from this value here to give me 4/9 pi. If I add 3/9 to this value, I get to 4/9 pi too. So you can always double check that you found this coordinate correctly. Now we have to figure out this point and this coordinate here. So we want to take the distance here and cut that in half as well. So that would give you what, 3/9. So the distance there was 3/9, which we already knew. I shouldn't have even have asked. But we take that 3/9 pi, we cut that in half. Okay, and we end up with 3/18 pi. So I want to add 3/18 pi to 4/9 pi to figure out what that value is. I also want to take pi over 9 and add 3/18 pi to that as well. Okay, to figure out what that point is here. So let's do the first one. Pi over 9 plus 3/18 pi gives me 5/18. So I have 5/18 pi here. 4/9 pi plus 3/18 pi gives me 11/18 pi. Okay, so I know that these kind of stink because they're fractions, but it's not hard. It's just, you gotta just know how to add and subtract fractions and multiply and divide them. Okay, so anyhow, there's our graph so far. Now the only thing I have to make sure I do, or not only thing, but I have to make sure that I take into account the fact that this is now an amplitude of 2, so I have a max height of 2 and a minimum of 2, -2. Now, this plus 4 here would cause us to shift every single point up 4 units. That would stink if we had to redraw this and go, to 6 here and do this all over again. So here's a really cool way to change that. Just add 4 to your max and add 4 to your min. So now this is actually at 2. This is actually at 6. So I just shifted everything up by just changing my axis here. So I don't really have the y. This is not the x-axis here. It's actually down here. So you can always redraw that in. But this is the sketch that we want, okay? That's the end of number 3. It's a monster, but it's doable for sure. Okay, problem 4 is another tricky one here. It's got a lot of different transformations going on. And actually the 2 here is not really in our general shape that we looked at before. So make sure you notice that this is really just plus 2 at the end here. So let's just cross that out. Okay, now when I graph a regular cosine function, I start here at 0, 1, I come down, back through, and I end here up at 1 again. But in this case, because I have this negative, it's going to reflect over the x-axis, which means that it's actually going to look like this. Okay, so I'm going to erase that guy. I'm also going to erase the y-axis here because I don't know where it starts and where it stops. So to figure that out, I set this and I trap that between 0 and 2 pi. So that's 0 is less than or equal to pi x plus 5/6 pi. and I solve for x. So I subtract 5/6 on both sides, and 12/6 minus 5/6 gives me 7/6 pi. Divide by pi now on both sides, and I end up with negative 5/6 is less than x is less than 7/6. Okay, so I start at negative 5/6 and I end at 7/6. Now the distance between these values is 12/6, or just 2. So my overall period here is 2, which means that this point here on that axis of equilibrium here is 1 unit away from 7/6. So I subtract 1 here to get 1/6. Now I want to find these two values here. Since this is half, or 1/2 here, this is the distance between 1/6 and this coordinate, I'm going to add 1/2 or 3/6 here, and I get 4/6, which means that this number is 2/3. Okay, I would subtract then, or add, I guess, 3/6 here too, right, to get this point here, and that would give me negative 2/6, or negative 1/3. Okay. Okay, now all that's left is to figure out the y-axis here. So let's draw that in. It's going to be between here. Okay. So it's between there, obviously, because that's negative 1/3. That's positive 1/6. So it's somewhere in between. Now we do not need to find the y-intercept or the x-intercepts for this function because that's something that we're going to learn in a later chapter. Anyhow, you don't have the skills yet to solve for this quite yet. But basically, what we're going to do is start with our amplitude that's been adjusted. So now instead of being at 1 and negative 1, this is 3 and negative 3. Then I look at this plus 2 here. I factor that in by adding 2 to both of these values so that I get 5 here and negative 1 here. So you could draw in your x-axis also. So my x-axis would be somewhere like here. But that's really all we want, is this sketch here. Okay, so that's the end of that one. Okay, please pause and try 5 and 6. You definitely want to try these to make sure that you know what you're doing, because there is a lot of stuff involved in this, and the transformations are definitely not easy with the fractions. So please make sure you try 5 and 6, pause and check with the key. So in the last part of the lesson here, we're going to be writing an equation when we're just given a graph. But I want you to notice that in the directions here, it actually specifically tells you that the pictures below depict sine functions. Because otherwise you wouldn't have any idea if it's a cosine or sine function, because they take the general same shape. So in this case, we're going to focus on just writing a sine function to represent, let's start with number 7. Alright, so I know that the sine wave comes in this general form here. Okay, but it looks like I haven't translated anything up or down because I'm at the horizontal axis here, so I can get rid of that because it's just plus 0 here. I also noticed that the amplitude here, it's vertically stretched by a factor of 3, so my amplitude here should be positive 3, also because I haven't graphed it. I don't see a graph that looks like a reflection of the sine graph, so it's going to be a positive 3. So I have y equals 3 times the sine of some quantity here, bx minus c. Okay, now, to be able to find that value here, I'm going to take a look at this coordinate and the x value. Now this point here represents 3/4 of a full period. Right? This is the 3/4 point of a full period. So I can say that 5/4 pi is equal to 3/4 of my full period. If I want to find the full period, I'll then have the stop, or the end for that full wave here. So let's multiply by 4/3. So we have 5/3 pi is 1 full period, which means that that coordinate here would be 5/3 pi 0. Okay, so that's helpful. Now what we're going to do is go back to that idea that when we originally start, when we graph a sine function, when we look at the phase shift, we set bx minus c, that value, we encapsulate that between 0 and 2 pi, right? Eventually, we add c to both sides, and then we divide by b. So we add c here. So we have c is less than or equal to bx is less than or equal to 2 pi, and then we finally divide by by b to figure out where our start and our stop values are. Okay. So what we're going to do is the same idea. We're going to work backwards though, because we have this. We want to know where it what our original bx minus c looks like. So right now we know what x is trapped between. We know that x is trapped between 0 and 5/3 pi. 1 full period, right? X is trapped between 0 and 5/3 pi. I want to work my way back so that I end up with this. Okay, so I want to find how I can transform this into this statement here. So I want to find what that's going to end up looking like. So let's start. Obviously, I don't have to add or subtract anything to get that 0 to stay 0 on one side. Really, all I need to do is adjust this 5/3 pi. So I want to get from 2 pi to 5/3 pi. Well, I would have to multiply that 5/3 pi by some value. I'm going to call that, let's use a totally different variable for it, z. Okay, so I want to find what I need to multiply that value by. So I'm going to divide by 3/5 here, or multiply by 3/5 here to get 6/5 pi. In other words, I have to multiply this value by 6/5 in order to get to 2 pi. So if I multiply by 6/5, I need to make sure, or 6/5 pi, oops, sorry, it's just 6/5. I need to make sure I'm doing that for everything here. Multiplying this by 6/5 stays 0. Multiplying this by 6/5 gives me 6/5 x is less than or equal to 2 pi. So I just found what the original value was inside here for this phase shift. This bx minus c is 6/5 x. So the equation here is y equals 3 times the sine of 6/5 x. Now, I know that looked pretty confusing. We're going to do another one, but the general idea is to start with what you know. So you find your start and your stop, and then you work your way backwards so that you come up with this general form here. So let's do a different one. This one has a totally different feel to it, since the graph here is a bunch of data, and it doesn't give you a defined point, so we're going to have to find that for ourselves. Okay, so I know it's a sine function. What I want you to do first is try to identify where the midline or the equilibrium axis would be. So here, I draw that in. Looks like I have a clear, let's just pick any start point here. A clear start point here at 10. Let's call that 1060. And an end at this time we're going to just estimate. Let's make that 2260. Okay, so here are the two coordinates here that represent 1 full period. Okay. All right, now I'm going to start with the general form y equals a times the sine of bx minus c plus d. Now, I definitely do have a vertical shift up, because you can see that this is not centered around the x-axis. Now, in some respects, this problem is actually easier than the last problem because we didn't have to figure out what our period is. We can clearly see our period starts at 10. Okay, and ends at 22. So right now we have this here would help us to graph this function, right? We would work our way from this general shape, or this general form of 0 is less than or equal to bx minus c is less than or equal to 2 pi, and we'd end up with this after we added the c and the b. So what we want to do is work our way backwards. What was that original start? Well, let's manipulate this so that we can get there. The first thing we want to do is try to get 0 on our left side here, which means I'm going to subtract 10 from all sides. So I have x minus 10 is less than or equal to 22 minus 10, which is 12. Now, from 12, I need to somehow get to 2 pi, right? So eventually I want this form. Again, I'm stressing that we want to work our way backwards and get back to this form. So to get from 12 to 2 pi, you need to multiply by some value. I think we were calling it z the last time. So 12 times some value to get you to 2 pi. That value is going to be 1/6. I'm sorry, 1/6 pi, right? So if I solve for z here, I would divide by 12, and I get z is equal to 1/6 pi. So that means that I need to multiply everything here by 1/6 pi, okay? Which now gives me 2 pi on the right-hand side. I still have the 0 here, but this inside here needs to be multiplied by 1/6 pi. So you're going to distribute to both. So you have 1/6 pi x, or just pi x over 6. Let's call it that. It's a little bit cleaner. And then 10/6 pi, so that's 5/3 pi. So you're just distributing the 1/6 times -10. So this would be that phase shift here, which would cause that phase shift. So pi x over 6 minus 5/3 pi is going to go on the inside all the way back up here. Okay, so we have y equals a times, a times sine of pi x over 6 minus 5/3 pi. And then let's talk about what the a and our d values are. Okay, so to find our amplitude, what we want to do is figure out our max and our min. Okay, it looks like above the axis of equilibrium here, we're moving, I don't know, let's call that point, let's say that the y value here is 70. That looks about right. Okay, so it doesn't matter really what the x value is, but since we're moving 10 units up, that means my amplitude here has to be 10, because again, if you look down here, this graph, or this point here is that y value, the minimum here is 50. So we've got an amplitude overall of 10. So right now let's just plug that in here. But we also notice our sine function, actually this is not reflected, right? I was going to say it's reflected, but it's not. It follows this general shape, so it hasn't been reflected, don't need a negative there. Now let's talk about how it's shifted up. It is shifted up 60 units, where our axis of equilibrium is. Okay, so it's plus 60. So this is a pretty difficult type of question here. It starts off a little bit easier than the last one because we're clearly defining for you what the period is just by selecting coordinates. But then you have to really consider how that phase shift is being affected, or how it's affecting your graph, I should say, and then finding those values, working your way backwards. So start with what you know, start and stop, try to work your way so that you end up with it trapped between 0 and 2 pi. Okay, we'll get a lot of practice with this, but that's the end of the lesson. See you guys tomorrow in class.